I hope everyone's doing well. Thank you for joining me for this video where we are looking here at another style of non-homogeneous or inhomogeneous second order differential equations where your expression equals something which is trigonometric. Non-homogeneous differential equation, and it's equal to a certain function, and that function is a trigonometric function. And what do? If your function over here is equal to something like, let's say, k sine x or something like k cosine x, here what we're seeing is a k sine x, and these x over here can even have a constant or a coefficient. As you can see, it's not just sine x but it's sine 2x. But if you have something like this, then you're using the template which is going to be c cosine x plus d sine x, where these x's in addition can have a coefficient. As you would see a 2, you bring a 2. But look over here, this is exactly what you're doing. You're seeing something like this, your function is equal to a trigonometric function, then you're using this as your template, and this is what y will be equal to. And all of this is necessary to determine your particular integral. The complementary function part analysis is easy. You're just using a basic homogeneous techniques. This template is what you will do for your particular integral. So when you're looking over here at this specific question, we have a y double prime plus 6y single prime plus 10y. This here is the second order. It's a differential equation, but it's inhomogeneous or non-homogeneous because it's not equal to 0, it's equal to a function, and here this function is a trigonometric function. So we have to analyze it and determine the general solution. A single example for this video will suffice, because when you're doing the particular integral determination, it can become messy and complex because of the systems of linear equations becomes a long task. Hence, to keep this video in a good length, we'll do a single example, but it should suffice that one example will show you the technique for solving these style of equations. We are going to start here with the determination of the complementary function, and for that we're focusing only on the left hand side. We have this, and that's all you're focusing on. And we have obviously our templates. Y equals e to the rx. The first order is r e to the rx. The second order is r squared e to the rx. You plug it in. You're always equaling it to 0 because you're determining the complementary function using your homogeneous techniques. I have an r squared e to the rx plus 6r e to the rx plus 10 e to the rx is equal to 0. You can isolate e exponent rx. You have a r squared plus 6r plus 10 is equal to 0. You can take this on the other side, it'll 0 out. But here you're looking at something which cannot be factored. You have to use your quadratic formula. A, b, and c, minus b plus and minus square root b squared minus 4ac over 2a. You have to use that. You have a, b, and c. You have a minus 6 plus and minus b squared, which is 36, minus 4ac, which is a 4d, divided by 2. When you simplify it, you have a minus 6 plus and minus square root of a minus 4 over 2. Simplified further, you have a minus 6 plus and minus 2i over 2. Simplified even further, you have a minus 3 plus and minus I. This is what I have. These are my solutions, but these solutions are complex conjugates. You have a and a b, and the template for that is slightly different than if you had two real solutions. Your template for something like this is what? You're going to have y is equal to e exponent ax, then you'll have here a constant cosine bx plus another constant sine bx. You have a minus 3 plus and minus I. This here is your a, this here is your b, lowercase. You plug it away. You have e exponent minus 3x because a is equal to minus 3. Then you have a cosine bx, b is equal to 1. There's a constant 1 here. You don't even have to write it, plus b sine x. This right here is our complementary function. Y is equal to, and it's done. That's what we needed, and we have it. Now we have to focus on the particular integral analysis, which is the hardest part of these style of questions. For the particular integral, you're focusing on the right hand side. We know for a function which is trigonometric, we have to use a template which looks like c cosine x plus d sine x. But these aren't just x's, there's a constant over here. You can do 2x and you can do 2x. This is what you have to use. Now you have to find the first and the second order derivative. When you find the first order derivative of this, cosine is a minus sine, and the 2 comes out. You have a minus 2c sine 2x. From here you have a 2 coming out, and a cosine, you'll have a 2d cosine 2x. Then you have to find the second order derivative and find the derivative of this. Sine will be a cosine. You'll have here a minus 4c cosine 2x. Cosine will bring out a negative. You'll have a minus 4d sine 2x. You know how to do this. This is nothing other than just basic derivatives. But this is where it'll get messy when you plug it into here places of double prime, single prime, and y, and then you solve it out. Systems of linear equations will become complex. So bring it in. Double prime is going to be minus 4c cosine 2x minus 4d sine 2x. 6 times these items. We'll do them in one shot. 6 times that minus 2 is a minus 12c sine 2x. 6 times this 2d is a plus 12d cosine 2x. I'll come over here. 10 times all of this will be a 10c cosine 2x plus 10d sine 2x. All of this is equal to what you see over here, 2 sine 2x. Now look over here how I'll isolate everything. I'm looking at all my cosine 2x components. That's what I have right here. When I look at these cosine 2x components, I can isolate them out, and I have here a minus 4c, I have a plus 12d, then I have a plus 10c. When I clean this out, I have a minus 4 plus 10, which is a 6c plus 12d. 6c plus 12d. 6c plus 12d. I've isolated the cosine 2x components, and I brought out their items, their constants before it, their coefficients. Now what I'm going to do is isolate the sine 2x components, which are everything else. When I look at the sine 2x components, I have here a minus 4d, then I have a minus 12c, and lastly I have a plus 10d. When you simplify this, you have a minus 12c plus 6d, minus 12c plus 6d, and we'll bring it in. All of this right here is still equal to this because we just algebraically manipulated items. We haven't removed any, but rearranged and rewritten. That's what we've done. Now we have to utilize these items here for determination of c and d. I'll erase everything else you don't need to see and only keep that what we need to continue. So how do we make this work? I know I have a sine 2x here and it's equal to sine 2x, so these items will equal that. Look, I have one linear equation which is minus 12c plus 6d is equal to 2. Because this right is a sine 2x component, here I've isolated sine 2x, so these items are related. I have a cosine 2x component, but there's no cosine 2x component after the equal sign, so it will equal 0. I have here a 6e plus 12d. This is what we have, and this is exactly what we need. We don't need to even see this anymore because everything is available for us right over here. We have to do our systems of linear equations. We'll multiply this by 2. I will have here minus 12c plus 6d is equal to 2. Then I have here a 12c plus 24d is equal to 0. I'll add these up. These cancel out. I have a 30d is equal to 2, and d is equal to 1 over 15, which is 2 over 30. C is equal to, well, plug away. Plug this d value in one of these equations. I'll pick this one right here. 6c plus 12d is equal to 0. 6c plus 12 times 1 over 15 is a 12 over 15 is equal to 0. Solve for c. I'll have a minus 12 over 15 divided by 6, which is what? You're going to simplify it out. You'll have a minus 2 over 15, and that's what c is equal to, minus 2 over 15. Now we have everything we needed. Keep in mind how these systems developed. We had our isolations of cosine 2x components, then we isolated our sine 2x components, and we equal them to appropriate items. Sine 2x items were equal to this constant right here because we had that. Cosine 2x was equal to 0 because we don't see any cosine 2x, and the systems are right here before you. We have the values of these constants. Now we plug away. What do we plug them into? Right over here, your basic equation, your basic template. Your particular integral is going to be y is equal to c minus 2 over 15 cosine 2x plus 1 over 15 sine 2x. You can even isolate a 1 over 15 outside, and then you can do sine 2x because it goes in at one time. There's a coefficient here 1, you don't need to even write it, minus the constant here will be a 2 cosine 2x, and here is our particular integral, and it should be right. Now we have to present our general solution. Marry up everything. Your general solution is equal to complementary function plus particular integral. My complementary function is this. I'll have e exponent minus 3x parentheses a cosine x plus b sine x. Keep in mind this is coming from your complex solutions minus 3 plus and minus I, which mirrors a plus and minus bi. Hence you're seeing your a and your b right here, ones. These capitalized a and b's are just constants. You have a second order differential equation, therefore you must have two different arbitrary constants presented, and that's what we have, plus your particular integral 1 over 15. and then you'll just write this out and you'll be done. You have a sine 2x minus 2 cosine 2x, and here is our solution, and it should be right. E exponent minus 3x parentheses a cosine x plus b sine x plus 1 over 15 sine 2x minus 2 cosine 2x, my complementary function, my particular integral, all of it equaling your general solution, which you know you can say y is equal to all of that, and we are done. Thank you for watching. Have a good day.